It's everybody. Sorry.
Probably
Thanks
first
for pulling
record
off week
ever.
10. Things are, needless to say, a little hectic for me. Yeah, it's been rough. I have, to very briefly explain, have had grad school apps, and I have, well, to prepare now for, and I'm sure you guys are as well, in the middle of exam season. So, sorry for that. I know the presentation today says we're going to be doing neural networks, but I don't know if that's a smart choice, because we haven't exactly covered a lot of stuff that we intended to cover last time. We talked about linear classifiers, if you guys remember, and right, we talked about linear classifiers. We talked about binary linear classifiers. We didn't get to multi-class classifiers, and we didn't get to logistic regression either, right? Which is a core linear classification model. So I don't think it's a good idea for me to skip straight into neural networks, because I think, as I've been trying to show the entire time, there is a sort of series of regressions that I think are kind of required. And I also want to do the neural network presentation like properly. So I'll, like, during the break, prepare actual proper slides, right? In which, like, I'll sort of hopefully go over the concepts that we went over this quarter. So I think today we'll try to go over logistic regression, multi-class classification, and also we can get to a recap of, like, certain concepts that we missed, or concepts that I did not cover from over the following past weeks. Is that fine with you guys? Okay, sorry, as you can tell, I have sort of hauled ass, as one says. So I'm still trying to catch my breath, and therefore you will hear me yapping in the middle of all this. Okay, why is this not loading? Okay, that's fine. Yes, and I'm sort of in the doghouse right now. So I need to lock in real quick. Okay, so can someone sort of tell me, like, what we talked about last time? Like, what exactly is a linear class is a binary linear classifier? Like, we gave a mathematical definition. So can someone sort of tell me what the mathematical definition of a binary linear classifier is? Anybody? Shout it out.
It's turning some inputs into either one or a zero through some kind of classification function that defines some threshold for when does it become a one or when does it become zero, and then based on that, it's what class have you assigned to one and what class have you assigned to zero.
Correct. Can you give me a sort of formula that we might say? Like, what if, like, how, like, if I told you to give me the binary linear classifier, namely the perceptron we talked about last time, like, how would you define it? Like, if I gave you an input vector X and Rn, like, I gave you, remember, like, the whole mathematical notation? I think that's sort of important because, like, well, what did it involve? What did it involve, at least?
Let's see, it was a matrix of thetas, and then it was a matrix of the input parameters x.
Correct. So you have an input vector X. To technical correction, it's not, you can't call them input parameters. It's because, like, yes, the function is parameterized by your inputs, but we don't call them parameters, we just call them inputs. Right? So input vectors, right? And then yes, you also had not technically a matrix, yes, but a row vector or a column vector, depending on how you orient it, of parameters. And then that produced what we called a, that's the neural network term, right? Like, when you refer to a certain node, the term I like to use is a linear response, because it very clearly specifies that, like, well, you're effectively performing linear regression, like, or like you're calculating a sort of like a weighted combination. Like, there's linearity, right? So I like to use the term linear response, and it's the term that was taught to me like via 178 with Euler. So linear response, right? You calculate a linear response, and then you apply some sort of blank function. Blank function, fill in the blank. Hmm?
Threshold.
Threshold is correct. That's yes, yeah. I like to more generally just like for a linear classifier in general, like remember a classification function is one in which it produces uh a output like one through, or how to say it, it produces discrete outputs. Like yeah, it's like a classification function. So in this case, our thresholding function is our classification function because what was the thresholding function doing?
-1, 0, 1.
Is that defining of like define the function for me?
Is it a step function?
It's a step function, but step functions have definitions. So give me the definition of the step of this sort of step function that we talked about last time.
1 is if x is greater than or equal to 0, and then -1, x is less than 0.
Perfect. Okay, yeah. So that's our linear classifier. Does everybody sort of remember that? Remember like how we gave the taxonomy? Like there was we had a so-called linear classifier, which, as the name suggests, classification produces an output like given it some input vector, we're producing an output vector in like a discrete output vector, right? Or a discrete output, right? It's one output of k possible outputs. It's not continuous, it's not real valued, it's usually discrete, as the name implies, classification. I am, for example, if I take an image, you tell me to classify the object in the image, right? I could classify human, chair, clock, right? Stuff like that, discrete things. So that's what classification is doing. And linear implies there's some sort of, well, linear function involved, right?
Threshold.
The linear exists in the linear response, remember? Which is why I like using these terms because you can sort of see that how they're all connected. Right? So there's a linear response. The thresholding function is not where the linearity is, it's where the classification is. We are turning a linear response into a classification, into a label 0 or 1, right? Yes.
When we say that it's a linear response, is that because we're tying it into the fact that it's like a continuous number through like a linear function?
It's like yes. More succinctly, well, you're applying effectively what is a linear regression model onto your input vector.
Okay, so
Right?
you're saying
That's where the linearity is. That you're applying a linear regression function effectively, like the formula used for linear regression,
Oh.
right? And as you know, linear regression fits a hyperplane through your data points. Okay, so okay. Let's see. And so we talked about that. Can someone? Oh, sorry. It's dead. No. Is there no good markers here? Is that visible or no? Okay. We will deal with it. So we have defined our linear classification function as follows.
Just gonna zoom in the camera.
yeah, no problem.
everyone remember this sort of formulation? This is what we've been describing, right? And so we talked about something called a decision boundary. Can someone tell me what a decision boundary is? Yes.
It's the threshold in which it becomes either a 1 or a 0, or in this case, a 1 or a -1.
Correct. It is as the name suggests, the boundary at which the decision changes. We can think of this is the classifier, right? This is in this case, in our taxonomy, it's a linear classifier. We have linear classifiers, we have binary linear classifiers. Binary linear classifiers produce one of two outputs. In this case, our two outputs is either -1 or 1, right? So in this case, this is a binary linear classifier, and specifically, we refer to this binary linear classifier as a perceptron because the threshold function is this Heaviside step function, right? In which you output 1 when it's greater than 0 and -1 when it's less than 0. Technically, it's not Heaviside, it's specifically Heaviside when it's 0, when you output 0 when it's less than 0. But if I remember correctly, I did this for mathematical reasons. But it doesn't matter, right? The point is there are two outputs, correct? Okay. And then a decision boundary is the location or the values in feature space in which your classifier's decision changes, right? So can someone tell me where this decision boundary is located? We talked about this last time.
Here.
When the input to x is 0, or when the input to t is 0, yes, but specifically where in feature space? Remember, it's an equation, right? I'm not sure if you guys remember. I was like sort of jumping up and down here. There's an individual sat here who isn't here today, but they were like, it's this formula, right? And I was like, yep, correct. Can someone sort of remember? You're on the right track. That like when the input to this is 0, that is where the decision boundary changes. But I'm asking where in feature space, right? Remember, we have, like for example, if I have two features, like I might have a decision boundary here in which everything to the left of this is evaluated at like 1, and everything to the right of this is evaluated at -1. So what's the equation for this? Very quickly. Yes.
Theta.x equals 0.
Correct. Yes. Correct. Does everybody understand that?
Can you write that out?
When the decision boundary is when theta dot x, in this case, like let's say our x is a column vector, so let's just call it like this: theta transpose x equals this. Linear response is 0. That's where the decision changes, right? We good? So
I'm still writing that
down. So recall. So one common question that people have is like, well, what do you actually classify? Like, or like, what do you classify? Like, what is the classification when I give you an input vector? So like, when I give you any x, it lies along this plane. Everyone get that? Right? If I give you an x that lies along this decision boundary, the location at which like the decision actually changes, well, what should you actually classify it as? We also talked about this.
It doesn't matter.
Correct. It does not matter. It does not matter. Well, to be more nuanced, it does not matter when when at least one of your features is continuous.
Yeah, because the probability is so low that you get exactly on the line that you won't ever have to worry about it.
It isn't just low, it's mathematically 0. Like when you, correct, yeah, if you take 170, if you take like 177 or 50, what's the stats class again?
67.
67.
Oh
God, it's taking him.
my bad.
He's been claimed.
When you guys take stats 67, yeah, like you'll know that the probability of actually equaling like of like a continuous random variable equaling a certain value, like it's just zero, right? So in this case, it doesn't really matter, right? Like if you just so happen to like luck onto like a feature vector that lands there, it's like, okay, mathematically genuine, right? So we talked about that, and then we talked about feature transforms and like how like because right now like remember how we like in previous lectures we talked about like how we can use a linear regression model to perform a we can use a linear regression model to fit a nonlinear function. Everyone sort of remember that like that discussion. How did we do it? I'm looking at you.
Feature transformation.
Yes, but
Feature
yeah,
transformation.
I saw you mouth it, so we're good. Yeah, correct, right? Like the idea of the feature transformation is like we are changing the data itself to like, namely in this case, we introduce extra dimensions into the data, like these synthetically generated dimensions, to like allow us to find a hyperplane that fits the data, right? And I don't know if you guys remember, but like David, remember, big buff dude. He like I was trying to draw it, and then he showed up like the laptop and the image, right? Like if you had like a quadratic function, right, and you introduced like, or how do you say it? You applied a feature transform that maps like, for example, certain xy values, right, certain xy pairs into one x squared y pairs, like our tuples, right? You went in this dimension, you introduced extra dimensionality in which now you can fit a hyperplane, right? We sort of talked about this, and this allows you to fit, well, like employ a linear regression model onto nonlinear data sets, right? And so similarly, we talked about like how we can induce nonlinear decision boundaries via feature transformation, right? Does everyone sort of remember that, right? And so we talked about like, if I told you, I want my decision boundary to be, let's say I have like a bunch of, let me think. My brain's a little blank today because I'm also hungry, really hungry. But all right, like if I want a circular decision boundary, right? Like how would I do that, right? So we might imagine, again, I have an actual marker. No. You got me?
Yeah.
Go. This is why the AI community exists. We give each other markers in times of need.
In times of need.
In times of need. Oh, my legend. Thank you. I will promise to take care of this. So, like, oh, wow, that's beautiful. All right, so like, recall we might be given like these x1, x2, y pairs, right? In which the y is like either 0 or -1 and 1, right? Everyone sort of remember this, right? So we might have data points scattered along here in which like it's either classified as 1 or -1, right? Usually we just represent them as circles and knots, right? So like I might have data points like dispersed like this or something like that, right? Like now, suppose like I said, like I noticed that like my data set sort of looks like this, right? And I want to fit a circular decision boundary, right? Because I'm like, okay, this is the best way to classify things, right? Like, how might I do that? Because right now, if I just use this plain linear regression model, or how do you say it, plain perceptron model, well then I'm going to produce, like as I said, the classification changes only when this is greater than or equal to 0, and only when this is less than or equal to 0. But we also know that this defines a line in hyperplane in this feature space, or like, yeah, right. So in other words, like we're at some point or at somewhere along this feature space, all the values along one side is going to be classified one thing, and the other is going to be classified the other class, right? That's like this generic. That's this generic perceptron model, right? And so this, we have to perform a feature transform. So can someone tell me what this feature transform is? I saw his hand raised first. So,
It'd be like theta x squared plus theta plus
well,
theta y squared plus
Remember-
theta. The formula for a circle, I'm forgetting off the top of my
okay,
head.
yeah, correct. Pretty much like a formula for
Yeah.
a circle, right? Like
X equals
you know
plus
that
It's like x
a
squared
fe-
plus
like you
y
know that your
squared.
feature transform is any sort of function Rn mapping to Rk, right? Like you take your input vectors, you take your input vector and then just apply this feature transform, right? In this case, I am saying I'm defining feature x, phi of x to be if I give you some sort of x1 x if I give you some sort of x1 x2 y tuple, I want this to equal 1 x1 squared x2 squared y, right? And then when I apply this feature transform phi onto this entire data set, and then I'll get like my transform features, right? Something like this, something along these lines. And then from there, when I apply the linear response onto this vector, I get theta 0, 1. That's our linear response. And then when this is equal, and then our decision boundary is when this linear response is equal to 0. Does everyone sort of remember this? Are we nodding our heads or are we genuinely understanding this?
Yes.
Okay, everyone seems to understand. Yes, Pratham.
what is the data, is that like the feature transform?
This is the feature transform. Remember, the feature transform is a function. It maps input features into a transformed input feature. Or it maps input vectors into a transformed input vector, right? That's just a function, right? I've applied this function onto all of our input vectors, right? And in this case, we define it to be 1 x1 squared x2 squared y. The reasoning being, when I actually apply linear regression, or when I actually try and fit a perceptron model onto this, right? Like when I actually evaluate the perceptron model, I am calculating first a linear response, right? My linear response is this dot producted with the parameter vector, which in this case is theta 0, theta 1, theta 2, right? For a linear regression model, right? And this produces, in our case, this formula, right? And we know that this formula is a good formula because, well, the decision boundary, like when we apply our thresholding function, right? So our binary or our perceptron would look like t theta 0 plus theta 1 x1 squared plus theta 2 x2 squared. Our perceptron looks like this, right? You give me any x1, x2 pairs, I can produce a classification using this function, right? And I can tell you where this classification changes precisely. We know that the threshold function changes when the threshold function is at 0, right? So when the input's at 0, right, that's where it changes. And when theta 0, theta 1 plus theta 1 x1 squared plus theta 2 x2 squared equals 0, well, that's the formula of a ellipse, right? In which a circle is a general, or is a specific version of, right? And so and so in other words, in this original feature space, our decision boundary is now an ellipse, right? So by inducing a feature transform, by generating a feature transform, we have induced a nonlinear decision boundary. Does that make sense? Yes.
What's the point of the theta 0 term?
It's like a bias in term.
Well, rare, it's a bias, but like, would that not matter for the thresholding function? Because, Wait, yeah.
What do you
Wouldn't it
mean?
not matter for the thresholding function because the thresholding function already takes like,
Well, when the
Well, let's say
thresholding
that's
function
zero.
is greater than zero,
It's a
right?
plus B.
But like,
right,
but
right.
it's like the sort of plus B in our.
Right.
in our language,
No, no, no,
Right,
yeah.
right, okay,
Makes
yeah,
sense,
good. Perfect, okay, so we've sort of recapped everything we talked about, great. Great, okay, Oh, yeah, and then we talked about, okay, yeah, this was the final note we ended on, right, which was like, well, like, remember, like, if I give you like this really janky, like, data set in which like there doesn't seem to be any sort of rhyme or reason. Oh, oh. With like how the data points are dispersed. Some people might just be like, oh, screw it. Like, let's just add a bunch of features. Or like, let's just add a bunch of artificial features via this feature transform, right? Can someone sort of tell me why we don't do that? Like why that might not be as good of an idea? Like why, like even for this for the original, like all the circles are on the outside and the x is on the inside. Technically, I could have defined a feature transform that mapped theta x, which accepts some x1, x2, y tuple into one x1 squared, x2 squared, x1 cubed, x2 cubed, x1 to the fourth, x2 to the fourth, and so on and so forth to whatever nth degree term I wanted. Right? Why don't we do that? You just walked in. Yeah.
Is this AI Club?
Yeah.
Oh, thank you.
Yes. Yeah.
It's
Overfitting.
Okay. Yeah. Correct. What does that exactly mean? Yes, it's a follow-up question. So yes.
It means that the model has so many like parameters that it makes its decisions based on the exact things you're testing it on and not the like underlying pattern essentially. So like instead of like instead of like there being like a line where there's like all the circles on this side and all the x's on this side, it's moving back and forth to include every circle or every x on one side of the line essentially.
Great way. of
And
putting
so
it,
it
yeah.
makes it useless for actual new data, which is what you would use.
Great way of sort of like phrasing it. Effectively, like you've introduced complexity, and when you like fit your model, right, to your data set, it'll do really well, right? Because you have enough complexity to learn complex relationships, right, as you minimize your cost function. But this additional complexity means it also takes into account like the inherent, like the noise of the data itself, right? And so the relationship that you learn is one that is very much influenced by noise, right? And so when you sample new data, then because your function fits so perfectly to the noise, right? It does really poorly on unseen examples, right? And so that's what we think of as overfitting. So in other words, yeah, in our case, when we induce extra dimensions, we've made it so that it becomes linearly separable in this really high dimensional space, right? That is like our data set becomes like we can fit a hyperplane such that everything in one side has one value and everything across another side has a different value, sure. But then it's so susceptible to noise, right? That it's very susceptible to noise because of this extra complexity. Okay, right? And so that's why it might not be a good idea. Like you want to introduce enough complexity to learn a good decision function, but you don't want to do it so much that you learn a perfect decision function and then on unseen data set, and on unseen data. Okay, so. Okay, yeah, so we talked about like how like a perceptron makes like classifications and like how we might like induce a nonlinear decision boundary, but we haven't actually talked about like how to train a perceptron, right? So like, can someone sort of recall the standard mechanism for training a machine learning model? Like this, we talked about this like third or fourth week, so it was quite a while ago, but this is important, so yeah. But like, what exactly, like walk me through the process, right? Like if I told you to build a machine, like if I told you to build a, like, if I told you to train a linear regression model, right? Like using the sort of framework that we've talked about, like how would you do it?
So, you like start from the output and then like create like kind of like just find the derivative of the output with respect.
Let's step back first. We have like, for a linear regression model, right? We have a bunch of data points. Initially, I have to somehow put a line on the map, right? A line on this graph, right? What does this line? What is this line? Can it be?
You probably just like, I don't know, sample it from a random distribution.
It can be anything. Yes, exactly, precisely. It can be anything. But then what are you doing next? Like from that point onwards? Like you mentioned derivative very quickly, but you
Oh,
weren't
right.
mentioning
Well,
what you're
we-
actually doing.
Gradient descent.
We're mentioning keywords now. What exactly, like, so walk me through step by step. What are we doing?
Test it.
First, you.
What are we testing?
Testing how well the line fits the data, or and how close the hyperplane is to each
How?
of the points.
There's a
mean
specific-
squared error.
Correct. There we go. Yes.
Just at least squares regression line.
We calculate the, like, we calculate the MSE, right? I give you a bunch of data points, plop any random line on there or any hyperplane on there. Tell me using MSE how far it is, right? Like that is our cost, right? That is a way of evaluating how poor our model is, right? Technically, this doesn't like. You don't actually need the exact cost function, like the value of the cost function at that point, but like intuitively what you're doing, right? Like from a mental model, you're saying like, okay, I make a prediction, like, or how to say, I have a predictive function, right? In this case, it's our linear regression model. It's our hyperplane in this feature space, right? I calculate how poor this prediction is, right? And then I take a step in parameter space, which like minimizes this cost, right? That's our gradient descent, right? But in this calculation of like minimizing this or moving in parameter space to minimize the cost, we actually don't need the value of the cost function itself in this case, right? You will need error terms though. So yeah, so gradient descent, right? We initial so to be more specific, like the sort of like way we think of it is like we initialize a set of parameters theta randomly, right? In this feature in parameter space, and this corresponds to like a hyperplane through features through our data set, and then we calculate the gradient, if you guys remember, and then we take a step along that gradient. Slow head nods. What's the thought?
I didn't.
Oh, are we good?
Yeah.
Okay, good. Yeah. But there's an issue with this, like when we do it with like what is the sort of natural cost function for a classification model? Right, like
It's, or well, it would be cross entropy cost, right?
well, I mean, intuitively speaking, if I told you to classify a model, right? Like if I told you to calculate the error of a model, right? Like how would you calculate the error of the model? Like very intuitively.
Do you mean like just
How
mean
far
error?
away your expected is from the actual,
For a classification model.
whether or not it's right or not?
Correct. Your percentage correctness, right? Right. But like, can. In this case, like, our cost function would just be,
You right, you wrong.
Hmm?
Just you right, you wrong.
right, this part is is like the indicator function. I give you an error of 1 when your predicted output is different from your actual output, right? Go through each data point. So go through each data point, add 1 if they differ, if your output differs from your prediction. Right? If like the actual output, or like the actual label differs from your predictions. Add 1. Find the mean. Does that make sense? Right? This gives you percentage error. Right? Like how many did you get? Like what is the percentage that you got wrong? Does that make sense? Can someone find the gradient of this?
No.
Would it be a number between 0 and 1?
No, because there is no. Wait.
Right? Y I hat, our prediction, the label is the same thing as this, right? Can you find the gradient of this? Is it possible? Why not?
Not like a differentiable.
Step.
Yeah, there are issues with differentiability, yes.
It's like not even, it's not even a step function, like, I don't even know how you grasp it.
It is piecewise constant.
Yeah.
Right? Think about it. You might imagine that I am fitting, like, or how do you say it? Remember, the decision boundary is like when the decision boundary equals 0, or how do you say it? Or the decision boundary is defined by when this is equal to 0, right? And that forms a line in this feature space, right? And as I shift the parameters around, right, this shifts the nature of this line, right? Like how the hyperplane is like oriented, right? If I shift it enough, right, then at some point, I might like shift, for example, this hyperplane to a point where, like, imagine this is a straight line, like it cuts through a data point correctly, and it changes the prediction, or how do you say it? It changes the prediction of a input feature, right? So like, what I'm saying is, sorry, my explanation here is a little cruddy. My decision boundary in this case is aligned through this feature space, right? As I change my parameters, I am changing this decision boundary, right? At some point, I will, like, for example, let's say I have been, like, it starts off here. So in other words, everything towards one side is predicting one value. Everything to the other side is predicting a different value, right? If I shift this line to now like here, what happens? Like, I might have changed the prediction for one value, right? And when I change the prediction of one value, I alter my cost by some percentage, right? But like from within like this region, like for all parameters, such that, how do you say it, everything's still classified to one side, the cost doesn't change, right? Notice for all of these lines, right? Everything is such that like everything is position, or how do you say it? The decision boundary places all points to one side of the decision boundary and no points to the other side, right? And so the cost is constant, right? Does that make sense? Are we confused here? Be very serious, like genuinely, if you need me to re-explain this, yeah, what?
Can you please read?
Okay. A decision boundary is the location, or is the, like, the set of points for which, like, at one side of the points, it makes a certain classification, and for other side, it makes a different classification, right? When I initialize, like, in this case, we said our decision boundary is given by this when the linear response is equal to 0, right? And when the linear response is equal to 0, it forms a hyperplane in feature space.
Because that's the equation.
That's the equation of theta 0 plus theta 1 x1 plus theta xn equals
It's
0.
just a bunch of weights and bias.
It's a bias plus these n weights, right? This when this is equal to 0, or in this case, it's when theta 0 plus theta 1 x1 plus theta 2 x2 equals 0, which if you plot it out, gives you a line, right, in x1, x2 space, right? Everything across on one side, in this case, for this specific decision boundary, is predicted, let's say like we're predicting it 1, right? Let's say everything across to the left of this is 1, everything to the other side is -1, right? The cost is some value. What if I alter the parameters a little bit? So it's like this. Does the cost change? Why not? You know why. You intuitively said no. So somewhere you deduced that it was no. Why? Why doesn't the cost change? And anybody?
Because you're still predicting the same values to be the same things.
Correct. Correct. So you can imagine, like, as I change this, right? Again, like, let's say I'm predicting 1, -1, 1 on this left side, -1 on this right side. I still haven't changed my predictions for all these values. So in other words, there are certain regions of parameter space in which my cost doesn't change, right? And then when I shift over, right, it might change to a different value, but again, for a certain slice of parameter space, the cost doesn't change. And so you can immediately tell intuitively that this is piecewise constant, right? In other words, in parameter space, in theta 0, theta 1, theta 2 space, right? There are certain regions of theta 0, theta 1, theta 2 that map to a constant cost, and other regions that map to a different cost. But they're all, but like within a certain region, they're constant, right? They're flat. And remember, the gradient is like finding the direction of greatest ascent. Well, if I'm on a flat plane, right? So in other words, that cost function, like intuitively sort of like looks like flat and then jumped up in certain region, and then like maybe lower in a different region, and then higher with like sharp discontinuities, right? At the points where like for example, right at like here, for example, if I move across just a tiny bit, then my cost immediately jumps to a different value, right? Does that make sense? Yeah. Does that make sense? Oh, wait. Yes. I don't know. Okay. Because sometimes I try to like I try to gauge the room. I try. You know? So like our cost function is piecewise constant, and so when we like, what's the gradient of a piecewise constant function? Zero almost everywhere. Zero almost everywhere.
Except for 0.
Those different areas.
0 almost everywhere except where the cost changes. When the cost changes, right? It's a discontinuity. You can't calculate the derivative of discontinuity. You can introduce something called subderivatives if the thing is, if the cost function is what we call convex, in which it looks like a bowl, right? But, yeah, no. And technically,
You're just a constant region.
actually, I talk about like, technically, like there is a way to, like, so in other words, like gradient descent is like kind of crappy because it's 0 everywhere. Like if the gradient is 0 everywhere, and remember how our gradient update works, right? We have an initial set of parameters theta, and then we subtract like a step value multiplied by the gradient, right? If the gradient is just a 0 vector, well then I'm never updating my parameter, my parameters. Does that make sense? Right? So the gradient of this is dog water. right? But like, how can we sort of ensure that our standard training methodologies still sort of work on our perceptron? Right, so if our training methodologies, like if our gradient training methodologies are struggling to optimize this sort of classification function or this classification error loss function, then maybe we should just try a different loss function, right? So we should remember a loss function is just a way of evaluating like the performance of a model, right? So instead, like we can employ what we call a surrogate loss function. So a surrogate loss function is an alternative loss function where like that replaces some original loss function that is difficult to optimize. So in this case, we've sort of like very intuitively shown that this is terrible to optimize over, right? Because this cost function in parameter space is piecewise constant, right? For certain regions of theta 0, theta 1, theta 2, the cost is 0. Like the cost is constant. And then for different regions, it suddenly spikes up or spikes down, right? And trying to find the gradient of something that is like flat everywhere, right? Effectively flat everywhere, right? It's just the gradient of that is always 0, right? Is that making sense?
Yeah.
So instead of using such a function, why don't I just use a different evaluation metric, right? Like we want, like notably sort of like the surrogate loss function still needs to represent like cost. In this case, like this is intuitive because we know like this is like our intuitive idea of like what poor classification is, right? Like you either get it right or you get it wrong, right? But we realize like when we represent it mathematically, optimizing over this is terrible, right? So instead, like we should define a loss function that is semantically similar, right? That like preserves this meaning of like, oh, this is poor performance, but like, and it should be similar in nature to like how we define cost, right? Like how we intuitively define cost. And but the difference is we want the surrogate loss function to be like easy to optimize, right? So and when we optimize over this sort of surrogate loss function, our hope, right, is that the original parameters of like for the surrogate loss function, or how do you say it? The optimal parameters for the surrogate loss function is equivalent or close enough to the optimal parameters in this terrible is close enough to the optimal parameters for the original loss function, right? So I have a terrible to optimize. I have a like here, like I can still have like a local minima, right? But like finding that local minima is terrible because the gradient's always 0, right? In this case, we define a loss function that is hopefully similar, both in semantic meaning, but also easy to optimize over, right? Such that when I find the optimal parameters using this alternative loss function, it's close to the optimal parameters here, right? Because this is what we really want to optimize, but we can't do it, so we just choose a different one that's close enough, right? Does that make sense? So the question then is, okay, like what's the actual surrogate loss function? Well, the surrogate loss function is what we call the perceptron loss function. Technically, like I'm choosing to present it this way because it makes, in my sense, more intuitive sense to me to present it this way. But like how some guy initially defined it was like he defined this perceptron, right? I think it's like 1960s or something. Defined the perceptron, he defined a training algorithm like that optimized the parameters directly, and then you could like, and then from there it implicitly defined a surrogate loss function. But it's harder to understand like where this gradient magically appears from. So I like to like tell you what the surrogate loss function is. So okay, everyone sort of remember this? Cool. This is like the classification error function, right? So instead, the perceptron loss function is defined like this. I don't think they actually go over in 178, I believe. It's a monstrosity. I'm not even gonna bother explaining like, how do you say it? I just want to show you it exists, right? Or like this surrogate loss function is a thing.
Circular loss function doesn't exist. He can't hear you. Circular loss function.
It's this. The heck? Whenever you sort of see this in a loss function, you sort of already know like you're averaging, right? You're averaging and you're iterating through each data point, right? What we're saying is like, okay, for each data point, give me the x, like, give me the x value, right? Or give me the x input vector. Calculate the linear response, right? And somehow this term gives me a cost, right? Somehow this term gives me a cost. But okay, I need to think this through. When my linear response is greater than or equal to 0, I'm predicting 1. So if this, if my y, so I'm predicting 1, if my actual y is also 1, right? Well, then this is a positive term. Y equals 1 is a positive term. So this yi theta xi transpose term is positive. I take the negative of that, it becomes negative, and the cost is 0. In other words, when I predict correctly, when theta x is greater than or equal to 0, I have no cost, right? When I predict -1, if theta x is less, actually, let's do, let's say if yi is -1, then what happens? Well, here I'm still predicting 1. Like, in this case, my prediction was wrong, right? If theta x is greater than or equal to 0, I'm still predicting 1, right? But if my my prediction is 1, but my actual label is -1, right? Well, then this term, this yi theta xi transpose term, gives me -1 times something positive is negative. Negative times another negative is positive. Max of 0 and positive is something positive. I have some cost. So if I predict wrong, I have some cost. If I don't predict wrong, then I'm good. Right? Yes.
Is that just a cost function?
This is a cost function. Exactly. Yes. This is an
It's
what I'm
just-
saying. What I'm saying is this is an alternative cost function to the classification error cost function that I just showed you.
What's the classifier?
The one that looked like had this weird 1 symbol, right? Where yi does not equal yi hat, which means give me like
Is it basically MSC but for classification?
no. It is literally percent correct or percent wrong.
Oh, accuracy was it?
It is percent error. It is 1 minus the accuracy.
Oh.
Right? But I'm telling you that that function was terrible to optimize on. Because the cost function is piecewise constant. By piecewise constant, I mean the cost is constant in certain areas of parameter space, and then suddenly jumps and is constant in a different area of parameter space.
Variable?
Hmm?
So it's variable.
It means the derivative, it means the gradient is 0.
Right.
It means it's flat, right? But the entire point of gradient descent is we need the cost function to not be flat so I can optimize over it, right? Because remember, my gradient descent is like theta minus some alpha term, the step size, times the gradient, right? And if my gradient is always 0, then theta minus alpha times 0, that's a 0 vector, is theta minus 0, which is just theta. In other words, I'm never performing an update. So if I use my classification error loss function to perform an update, I'm cooked. I'm not updating anything, right? So what we're saying is instead, we define another cost function, a surrogate cost function, which semantically still represents the idea of poor performance, right? We want it to emulate this behavior of classification error, right? Or at least from a intuitive point, right? But is easier to find the gradient of. It actually has a gradient, right? I'm not going to show you how this gradient, I'll show you later, but this is easy. Turns out this function is easier to find the gradient of, right? Like you can find an actual gradient and then perform updates. With a classification error, you couldn't. Does that make sense? Okay, yes.
Yeah, I was thinking that's something similar along to it. Is that don't you still run into the same problem as if you have different parameters theta that end up classifying all of your points to be the same cost, then wouldn't you still have piecewise constant loss in some
You have
region?
piecewise linear loss now. So you have this function, the issue, there's an issue with this function actually as well, right? You're pointing out an issue. This function looks something like this. This looks like a Rayleigh function, doesn't it? Right? Because it is a Rayleigh function. What is the derivative of this?
Positive,
It is 0 for all values that are less than 0,
and then positive.
and 1 for all values greater than 0. And then at this point, it's like code, right? It's not defined here.
You're right.
So you still sort of have an issue, but you have a different issue. But what I'm saying is okay. First, let's do you sort of understand this cost function? This cost function, first, I haven't actually fully explained it. If the linear response is greater than 0, you predict 1. So in either, right? So when your linear response is greater than 0, greater than or equal to 0, you predict 1. If your actual label is 1, then you're good, right? You've predicted correctly, you should incur no cost, right? And we're saying that this term becomes negative when you predict correctly, right? How? When when I predict correctly, which is this case, yi equals 1, theta x greater than or equals 0, it's positive. 1 times something positive is positive. Negative of something positive is negative. Max of 0 and negative is 0. I incur no cost when I predict correctly. Here, theta x greater than or equal to 0, I predict 1 still, but if my label is -1, I predicted incorrectly. I should have some sort of penalty, right? My penalty is theta xi transpose, right, is positive, yi is negative, negative times something positive is negative, negative times this negative term is positive. I've incurred a cost, right? And you can do the same for theta x is less than 0. In this case, in this case, what am I predicting? Shout it out.
1.
-1. If my theta x is less than 0, my threshold, if theta x is less than 0, remember, our thresholding function, right, when t of theta x is, or if I plug in theta x into t of x, right, if it's less than 0, if my input to my thresholding function is less than 0, then I predict -1. So I'm predicting -1. So in this case, if I have yi equals -1, let's say I predict correctly, what cost should I have? Hopefully 0. Correct. I should hope to have 0 cost, right? Does that make sense? Okay.
Yeah, because 0 is the greater value than 2.
Well, no, like intuitively, if I predict correctly, why should I incur cost? Right? Like what I'm saying is I'm trying to define a function. I'm trying to define a cost function, which is easier to optimize over, right?
So like a running total for like cost,
And then
like
you know,
you
sometimes
do
you can
add
write,
one
like,
when
static
you like
methods or whatnot.
predicting correctly, and then
static
add 0 if you
methods.
predict something correctly.
No, that's like
Maybe not.
if you predict correctly,
Have you
like so in
done-
classification error, when you predict correctly, like with this original loss function that we were talking about, when you predict correctly, you incur no cost, right? Like if I'm doing well, why should that ruin my performance, right?
This is
But if
essentially
I predict incorrectly, I should have some sort of penalty, right? Remember, a cost function should add some value, some penalty term
derivative
for
of
like
what it's actually doing.
misclassifying.
So here
right?
you're able to see if you at least if you never
Right.
decorated it.
So in this case, if I'm predicting correctly, I'm saying that like I've defined you a cost function that is easier to optimize, and in this case, it demonstrates the properties we want. When we predict correctly, we incur no cost. When we predict incorrectly, we incur some cost. Does that make sense?
And you're wrapping whatever this is on top.
So if I,
Yeah.
okay, so
It doesn't
Okay,
actually
let me
change any
think.
of the internals of this. It just wraps it in different stuff or puts it in different containers. Or maybe it does things.
I'm not gonna
before
show
it
you
runs, does
the
things
math,
before it runs.
but
Maybe
the idea
it
is
changes its output a little bit. It doesn't actually change what.
you can calculate the gradient of this, right? We still have issues here,
Say I want.
but it turns out, like it turns out that this cost function is
Either do it.
convex, right? It's piecewise linear, as you can tell. Like the max is well, it's a piecewise function and it's linear on both sides.
You have.
The sum of piecewise linear functions is still piecewise linear, right? And then dividing by a constant term still keeps it piecewise linear. So you can already tell that this has to be piecewise linear,
Doing.
right? Yeah.
How is it guaranteed that it's piecewise linear when?
you.
Or well, oh, right,
This
right,
is linear
because
as
art-
well.
That's linear.
This is linear as well.
Okay.
So it is piecewise linear.
Yeah.
You know, like analytically, it's piecewise linear.
Trying to take code that instead of.
And so if it's piece, like, and so it's convex as well. And because of the fact that it's convex, you can define something like, people are like, oh, like how do you find the gradient here?
Is more representative.
You use something called a subgradient, right? It is,
Understanding.
I'm not even bother like trying to explain it because I don't like think I can explain it well enough like to that like I sort of like I sort of kind of get it as well, but the idea is it's a sort of you can think of it as like I believe like as a set of slopes that still lie under this convex curve, right? So in this case, like this is a valid subgradient. Like this defines a supporting plane, which is a valid, or how do you say it? Which we can still think of as like tangent, right, to this plane. Because remember, a gradient is merely finding like a derivative is finding the slope of the tangent. So we still want to preserve this semantic meaning for convex functions, right? And so like anything that is, anything that's like remotely tangent qualifies as a subgradient. Pick any one as a as your gradient at that point. So if you encounter these sort of like kinks, right? Like these locations, like these kink points, then it's like, yeah, like you can still calculate a gradient for convex functions, right? So what I'm merely trying to say, the only reason why I've introduced this is instead of using the classification error loss function, we use this different loss function, right? We can still perform gradient descent because now we actually do have a gradient. Sure, the gradient is 0 when we're here, but here the gradient exists, right? Right, it's something because
It being convex is the issue, right? Because then the gradient drops really fast when you're like close to 0.
pardon?
Like the convex portion is the problem, right? Because the gradient starts dropping really fast when you get close to 0. And then you would just overshoot probably.
What do you mean by is the issue?
Well, because so you mentioned it's convex, right? So it looks kind of like a log.
A convex function looks like a bowl. A convex function is a bowl-shaped curve, pretty much, right? And we're saying like we can optimize over this bowl-shaped curve, right? Because you can find like a slope, right? You can find a gradient.
Are we saying that this max function is kind of like a bowl?
We're not saying it kind of is like a bowl. It is a bowl in a sense. Like bowl is a very loose term. Convexity just means like what was the exact precise term again?
Isn't convex like the rate of change of the derivative?
Yes, it's related to that. There's like the intuitive idea is like actually yes, no, it is that, right? For we say 2 points are right. We say like a function is convex if like the line segment between any 2 points on the graph of the function lies like above or on the graph between the 2 points. So I give you any 2 points here. It lies above the graph, right? if I do it for any of the 2 points, we can show that it is convex, right? And so convex functions have this property in which you can define a subgradient, right? Which is why, even though this is not differentiable here, I can define a gradient, right? And this allows me to perform gradient descent still, right? And in this case, the gradient exists and is non-zero.
Even though it's one constant value.
Yes, I just need something that can move. That is non-zero.
So then how would you,
Remember, our update function is like theta equals theta minus alpha times the gradient of our loss function, right?
Yeah.
As long as this is non-zero, I'm changing this.
yeah, but if you're changing it and then it's always just a constant,
There are issues with this approach. I'll describe them later, but
so it's just that you like keep doing it until you reach that zero or that minimized loss essentially. So
that's the hope.
So it doesn't necessarily matter that it's one same value. Since it's non-zero, you're moving it and you would eventually move it into that minimized
Yes,
parameters.
yes, but note, this is where we get into like the sort of quirks of this, right? Like I can find you the loss of it, or I can find you the gradient of this, and this defines what we call the like remember the SGD algorithm, right? The SGD algorithm says like you initialize your parameters randomly, you initialize your step, like you initialize this randomly, you initialize your alpha randomly, right? And then you perform this update continuously, right? Well, then we need to find the gradient of this, and it turns out the gradient of this bad boy is just for any given, like it's just minus y I xi. Like, or if the sub, like if you define the subgradient, I forget, like a certain way. If it's, or actually like if it's misclassified, you move, right? Because whenever, wait, let me explain. Let me see if I can explain this better. The point I'm merely trying to say is that instead of the original classification error loss function, I have defined a surrogate loss function. With this surrogate loss function, I can calculate a gradient, right? The reason I can calculate a gradient is because the original max, okay, remember, this is just a max function, right?
Yeah.
This is just a linear term,
Yeah.
right? I'm only performing multiplication, it's linear, right? A linear term in a max function is, well, a max, it's just a regular max function shifted, right? Max function shifted is a convex function. Sum of convex functions is convex. Divide by a convex term, or divide by a linear term is still convex. Okay? So I have a convex function, right? It doesn't matter what this looks like. It looks like I actually had a graph for this, but like
It looks scuffed.
it's just like a plane and then like weird slopes going up. That's what the loss function looks like in space, right? You might imagine. But it's better than the loss function that I showed you with classification error, right? Because classification error, it's flat always. It's zero always, or the gradient's zero always, except where like the cost changes. I can't even do optimization over that. I can't use this because if this is always zero, theta is never changing, right? So classification error has an issue. So instead I'm saying, I propose this function. I can calculate the gradient of this. Doesn't matter how, I can, right? And I showed you I can because first, the derivative of the max function, it like isn't zero everywhere, right? Gradient, like, so in other words, like, like sure, like there's a discontinuity here, but the property of convex functions, like allows me to define a subgradient, which like allows me to like just claim that
Ignore it.
like we can effectively say there's a gradient at this point. We just say it's the subgradient at that, right? Like we just choose we just choose a slope in which like it becomes a supporting hyperplane.
Because we have the property of convex, we're able to define some
Sure.
gradient and say it's good.
Like we can just say that there is, right? And then from there, right, I've defined a gradient that is non-zero. I can move. Simple as that. So in other words, but note critically, I didn't just choose a random I didn't just choose a random loss function, right? Like my loss function was defined to match our intuitive notion of what cost should be. You should just let it all. It costs, like I have a cost, right? When I predict incorrectly. I have no cost when I predict correctly, right? So this matches our classification error loss function, like I hope with the classification error loss function. Does that make sense? Okay, good. And so this results in like when you actually, when you use the when you calculate the subgradient, or when you calculate the gradient and use gradient descent, it gives you what we call this. I'll give you like the sort of
Congrats with your data better.
so much effort. Spend time on it. This is SGD, stochastic gradient descent, when our cost function is this. Okay. Note that this is just like our original theta equals theta minus alpha or alpha gradient of cost.
So if we're ever in a spot where our theta isn't being changed, can we essentially say, oh, our model's good? And then
Well,
we can just
but
stop?
we're iterating through each data point, right? Right, like we have to iterate through each data point. There is an issue with this. It turns out like for data sets which are not so-called linearly separable, I've been using this term for a bit. That is, and by linear separability, I just mean like if a data set is linearly separable, it means I can put a hyperplane through this feature space and perfectly classify everything. Okay. If our data set is not linearly separable, that means for whatever parameters I choose, there will always be at least one misclassified point. Okay. If our data set is like, note that this is like very ambiguous while not done.
It's pretty specific.
Right? Like, the heck does this mean? Hopefully, it means like we converge to a point where our loss function, or how do you say it? Our like nothing gets like theta gets unchanged always, right?
Converge.
It converges, correct? Our theta converges to a certain value.
That's what not.
Like our hope is like
Well,
like
theta
not
has not converged.
But yeah, while theta has not while our parameters have not converged to
Wait, is that the algorithm for S?
this is stochastic gradient descent. This is stochastic gradient descent in the case where our loss function is this. Right? Because stochastic gradient descent usually just says like, okay, update alpha and then this, right? But I'm saying like when you calculate the gradient of this, it becomes this. Like if it's misclassified, then you update. If it's correct, you don't change anything.
So does that mean that if it's not linearly separable, you'll always be changing things and you'll never stop?
Correct. 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 Yes. Very, very good. Yes, correct. 10 brownie points. I don't know. Whatever brownie
Gold
points are
stars.
worth. Gold stars. Yes. If this is what we call the perceptron learning algorithm. It is one of the first, well, learning outcomes ever proposed, actually. Right? some guy just proposed this off the bat. And then you can argue that the loss function of this loss function yields that. That's why I didn't want to show this first, because this comes out of nowhere, right? I wanted to show you that you can actually motivate this, right? You define a loss function that is semantically similar to our idea of classification error, that has a gradient. When we calculate the gradient, it gives us, like, we can update. Does that make sense? Okay. But there's an issue with this, as we said, which is if it's not linearly separable, if the data set's not linearly separable, if there are,
There's always going to be some error regardless of what you do.
if there's always some error regardless of what we do, if the data set's inherently like that, then by this rule, we will always update. And that's an issue, right? So convergence is cooked, right? And that's the fatal flaw of perceptrons and why nobody uses them pretty much, right? Because this sort of sounds like a great classification like algorithm at first, right? You're like, oh, this does well, but it doesn't because of this, right? Like even like this sort of surrogate loss function doesn't do well, and also like as we said, like the gradient doesn't look great, right?
So then are perceptrons only really used when like
I'm
in a very
trying to
specific like situation, and then you'd be like, okay, you need it.
I'm trying to motivate historically, like
How we got to where we
how
are.
we got to where we are.
Mhm.
And it's important because if I show you where we are, it doesn't allow you to think, I think, right? And so this is like why we define a logistic regression model, right? I know we have 5 minutes, but very briefly, a logistic regression model performs the following. So, wait, let me make sure I'm not missing anything first. Oh, right, yeah. I forgot to mention like some other cons of this, right? Like if the perceptron algorithms like guaranteed to converge for linearly separable, like you can prove that like the perceptron learning algorithm, this algorithm, is guaranteed to converge for linearly separable data sets, right, in finite time. But let's say you have a linearly separable data set, right? That is like we might be in feature space where if I define my decision, okay, here I have like very obvious decision boundary, right? Like the nicest one might be like somewhere like here, right? But our perceptron algorithm, depending on how we initialize, might end up like here or here, right? It's guaranteed to converge in finite time, and like because it's linearly separable, but it doesn't choose between optimal ones. Right? There's no notion of distance. And so these, like obviously, intuitively speaking, we want our decision boundary to be as far from our data points because this can be subject to perturbations, right? Like there could be noise, right? Right. So this perceptron learning algorithm doesn't do any of that, right? And so that's another reason it's bad. And then, like it's not necessary for classification tasks, but the perceptron algorithm, like the perceptron has no ability to quantify confidence through probabilities. It just tells you, right, whether something is like a certain class or something isn't. But like for a lot of applications, you might imagine, like does this patient have cancer? Like you don't want your classification model to just be like, yeah, like this patient has cancer. Well, how certain are you? That matters. Like if I'm a doctor and like I want like AI assistance, like I want you to tell me with how much percent confident. If it's 51% confident that it has cancer, it's very different from like the model being 99.9999999% confident that it's cancer, right? Like you want like in many cases you want some notion of confidence, and clearly you can see that matters, right? So we define a different model, right? That sort of resolves all these issues. The perceptron like. We introduce the logistic regression model. And the name is like kind of crap, but the logistic regression model is still like a type of linear classifier, right? It accepts an X, an input feature vector X, performs classification, right? And then also employs some sort of linear function, as the name implies, but does it in a way that is slightly different. Yeah, you produce a linear R remains the same. You produce a linear response, right? That's why I sort of call it R. Instead, your classification function, actually, your classification function f is now a decision function composed with a the logistic function. So the logistic function is defined as this. And that is a function that looks like that. Okay. And then we say when, and then the decision function is defined such that when
Is a sigmoid like a version of a logistic?
this is the sigmoid function.
Oh,
Is a logistic regression model just like a probability function or something?
What I'm saying is a logistic regression model is still a classification function. The name is crap. That's why I'm saying the name is crap. But where the logistic regression,
It doesn't look anything like a linear.
Hmm?
It doesn't look anything linear.
I'm saying that this function f, or this function f, remember, this is how we defined a linear classifier, right? Our function f in this, or our R of x is still our linear response, right? It is still this linear function we talked about. Our function f, in this case, is defined to be this, okay? This is still producing this linear response. The f applies a sigmoid function onto the linear response, and then applies a decision function or another sort of thresholding function at on the output of the sigmoid. Does that make sense? So in this case, the logistic regression model is calculate linear response, put it through sigmoid, put it through decision.
so logistic is all of those combined.
Yes, like it's in that order.
Is it just
Yeah,
like a
it's composition.
pipeline or
Hmm?
something?
What?
Is logistic regression model like a pipeline of action?
That's probably, yeah.
By function composition, yes. But technically, your perceptron is also a pipeline of actions too. If you're gonna, or composition, yes. Right. And we defined it such that if the x is greater than, I'm going to use p here because intuitively, the logistic this logistic function is outputting a probability of confidence. The decision function outputs 1 if p is greater than or equal to 0.5, and -1 if p is less than 0.5. Does that make sense? Right. Actually, be more precise. This helps. Actually, this accepts all reals, and then for sigmoid, converts is defined such that reals maps to. Okay, do we have enough time? No, we do not. Okay. Is that time? Okay. Okay, does everyone sort of understand like the point of like how to train a perceptron model? Because that's what we talked about today.
Yeah.
Good. All right. Sorry, that took a lot. That took a lot longer than I liked it to have. That taken, but hope that made sense.
Are neural networks kind of,
Long story short, very long story short. Logistic regression models you can think of each unit if you study neural networks, you can think of each unit in a logistic regression model as, or each unit in a neural network as a logistic regression model with it, without the decision.
It just has the,
Yeah, that's why it's called multi-layer perceptron. But the name perceptron also is a little off here because perceptron implies that you are using a thresholding function, but there is, like you're applying a thresholding function onto a linear response, but you're not doing that. So the name MLP is also tad off, like it's a bit of a misnomer. You're really calculating a linear response, applying a some sort of activation function, which in this case, like commonly we use the sigmoid, right? More often we use ReLU due to something called vanishing problem. And it's just those stacked together, right? So logistic, yeah. Yeah, that's pretty much it.
We'll be back.
Next quarter.
Next quarter, yeah.
are we
Thank you,
considering,
everybody. Good luck with exams.
do we have more workshops next quarter?
Of course. Yeah, but also something we're planning on doing more, it's like,